Dear students, welcome back to my YouTube channel. And you get my previous tutorial from my personal homepage or from my YouTube channel. It is shown here. Okay, we were discussing about the topic molecular rearrangement and transformation from the part reagents and transformation in organic chemistry. And today I am going to discuss with you a very important rearrangement, that is Favosky rearrangement. In my previous lecture, I discussed with you benzylic acid rearrangement. So Favosky rearrangement is a variant of benzylic acid rearrangement. So just to memorize what is, so do you remember what is benzylic acid rearrangement? And benzyl, that's alpha diketone, okay, and here this is alpha diketones. So diketone in the presence of hydroxide or alkoxide, in this case alkoxide, it gives an ester with a skeletal rearrangement. What are the changes in the product? You can see that this carbonyl is retained here, and you have an alkoxide group here in this carbonyl group, and R2 is migrated towards the next carbon, and that is here. This is R2, it moved to here, okay. Then this carbonyl become hydroxyl group. So here the rearrangement involves the breakage of carbonyl bond, okay. It is superficially it is similar the Favosky, but the mechanistically it is quite different. And you can see that this is an alpha haloketone. It react with the alkoxide. It give the same product. You can see it here. This is same product, and that is an ester. And here halogens can be used, chlorine or bromine or iodine derivative can be used. Here the rearrangement involves the breakage of CX bond. Here you have a breakage of CO bond, that's the difference. And product is the same as benzylic acid rearrangement. But I want to mention here mechanism is different from benzylic acid rearrangement. Okay, so this is the skeletal changes of Favosky, and you are started with alpha haloketone. The carbonyl group is retained here. Halogen is the left from this study material, and R group migrated to this halogen attached carbon atom, and alkoxide group attached to this carbonate. That is a skeletal difference, rearrangement that happens in Favosky. And in short, Favosky is a reaction of alpha haloketone. It gave exactly same product as benzylic acid, but a rearranged product when treated with alkoxide. And as I said, it is mechanistically different from benzylic acid rearrangement. So coming to the mechanism, and alpha haloketone with base, it gave first enolate. This is enolate, and this is alpha haloketone, and this hydrogen, it is highly this is little bit acidic hydrogen, alpha hydrogen, and in the presence of alkoxide, this alkoxide here it is not acting as a nucleophile, but it is acting as a base. So this base abstract this H plus, and it become carbanion, and it enolates like this. So you will lose a H plus here, and it form carbanion. Then this is the tautomer of this enolate. So this enolate, and this enolate will lose this Cl minus. So how does it lose? So here this it tried to restore this carbonyl, and this double bond break, and the carbanion will be formed, and that carbanion it attacked this the carbon atom with the chlorine, and chlorine will leave. Chloride anion is a good leaving group, and you get a product like this cyclopropanol. Okay, it is highly strained. So what is next? Alcohol side, this can act as a base and this can react, can act as a base, react with the carbonyl and the double bond break and it form an oxide anion or minus like this at tetrahedral intermediate will be formed and this anion restore and this is highly strained this cyclopropanone ring will cleave this one and it leave a carbanion and a carbanion will be formed. Okay, this double bond will form here. This bond, this transfers electron to this carbon and it form carbanion. Okay, right? This carbanion. And in the presence of solvent can give off its H plus to the carbanion and form finally an ester. Okay, next example, this is an alpha haloketone and this is uh, two isomers. You can see it here, one isomer here, this is the first one and this is the second isomer. And what is the difference is here chlorine is attached to this carbon atom, here chlorine is attached to this carbon atom. So in this alpha haloketone, in the presence of alkoxide, it gave the same product. It confused how does it form the same product. So it was found that the mechanism, the proposed mechanism for that reaction is like previous case, and here this proton is acidic. So this base can abstract this proton and it form an enolate. Then this enolate if it can give off this chloride anion as shown here, the mechanism is as shown here, and you get a cyclopropanone ring. So this is the first compound and you are getting a cyclopropanone ring like this. And second case also, second compound reactant, that is chlorine is here, this here, and this proton get abstracted by this alkoxide anion and it form an enolate, and after that it form a cyclopropanone ring as shown here. Okay, so both isomer give the same cyclopropanone ring, this one. So then finally what is the next step here? The one issue is here the next in the next step, which one is which bond will break here after the attack of alkoxide anion. So next step is the attack of alkoxide anion to the carbonate. So it form a tetrahedral intermediate, it form first and finally it restores oxide anion, and after restoring this oxide or CO double bond, which bond will break, whether this one or this one? That is a very important question. So here it open up to give ester product like this. Why it is giving this bond is breaking? Why it is this bond is breaking? Why not this one? Because if this bond is breaking, it leave a carbanion. That carbanion is this one, this carbanion. Okay, this carbanion is a benzyl carbanion. And if this bond is breaking, it leave a carbanion like this. This is alkyl carbanion. So compared to stability of alkyl carbanion and benzyl carbanion is more stable because this carbanion can stabilized by resonance. But alkyl carbanion, it destabilized this carbanion alkyl group. So it favors only this product. It favors the breakage of this carbon CC bond, not this one. Okay, and it end up with a product like this. So the direction of ring opening, the more stable carbanion forms. In the case of benzyl carbanion, it stabilizes the carbanion, but at the same time alkyl carbanion, it destabilizes the carbanion. We already know the stability of carbanion and stability of carbocation. The stability order of carbanion is tertiary is less stable than yes, less stable than secondary, which is less stable than primary. That is the order. more alkyl group, it can destabilize the carbanion. Okay, right. Next example is a rearrangement, Favorsky rearrangement by ring contraction. In this example, 2-chlorocyclohexanone with the methoxide, it gives methyl cyclopentane carboxylate, that is this one. So here you can see that one carbon is less in the product and you have an ester here. So what is the mechanism? This is the our study material. Okay, this is our study material. Alkoxide first abstract this proton alpha hydrogen and it form a carbanion like this. And next one, what happens is this carbanion form a cyclopropanone ring like this as previous case, and it leave this Br minus and it form a cyclopropanone ring. Next step is the second step. Second step, what happens? Alkoxide attack this carbonyl carbon and one of its bond CC bond break, and you can see that a cyclic product with one carbon less with an ester will be formed. You have how the ester formed. The alkoxide is attack this carbonyl carbon and it form an ester like this. Okay, similarly, next example, ring contraction example is conversion of cyclobutyl alpha bromo cyclobutyl into cyclopropyl ring through highly strained intermediate bicyclobutane. And you have an cyclic structure here, and in the presence of base, what happens is it can abstract this hydrogen here, this hydrogen, right? And it form a enolate, and after the enolate it form a cyclopropane ring like this, and this by attacking the water molecule you get an ester with a cyclopropane ring. So last example, rearrangement for ring contraction is this one. This is cycloheptanone alpha chloro, and you get an ester like this. And in this particular case also, first it get the proton alpha hydrogen get abstracted with this alkoxide and it form an enolate, and this enolate, what happens to this enolate, it form an intermediate cyclopropanone as shown here, and it leave this Cl minus. And finally, next step is the reaction of alkoxide. It can act as a nucleophile next. It attack the carbonyl carbon and SeO minus will be formed, and this electron restore its pi bond and one of its single bond will break and it form a carbanion structure with one carbon less than starting material. You have an hexane, a cyclohexane only here in the product, and finally on with alcoholic solvent, this carbanion will become they get this proton from this alcoholic solvent and you get an ester like this. Okay, in summary, and Favorsky reaction means it is a treatment of alpha haloketone possessing at least one alpha hydrogen atom with a base. It undergoes skeletal rearrangement via cyclopropanone intermediate, and finally it gives an carboxylic acid in some cases and ester also. And it is widely used for the synthesis of highly branched carboxylic acid or ester, and it is also a cyclic alpha ketone give a cyclic carboxylic acid or ester derivative, and cyclic alpha ketone undergo ring contraction and to form one carbon like cyclic carboxylic acid or ester derivative. Okay, that's all, and thank you for watching.